Alright, hi year 11s, this is Mr. Lim here again, and this is our next video on gases. It's Charles's law, so let's get started. Alright, so we're going to describe it, work out what happens when you change the temperature to the volume, and then we'll talk about this absolute zero. Okay, so what is Charles's law? It's the relationship between temperature and volume in a flexible container, and they have a proportional relationship. Okay, so let's talk about what happens. Okay, so let's go through our ideas about flexible containers and temperature. So increasing the temperature of a gas will increase the speed, and I really should say average speed, at which the particles move, right? And thus their average kinetic energy, right? And thus increasing the speed at which they move increases the frequency of collisions with container walls. Effectively, they are moving faster, therefore they'll hit the container walls more frequently. Right, increasing the frequency of collisions with the container walls increases the force at which is applied to those container walls. That's the interior force, right? And thus move them outward. Right, so they'll push harder on the inside, pushing them outwards, and this is only if the external pressure is kept constant. Okay, so by moving the container walls outwards, remember, now that you've moved the container walls outwards, the particles have to move further to collide with a wall. And by making them move further to collide with the wall, you actually decrease the frequency of collisions. And I probably should have written that there. Decreases the frequency of collisions. Okay, so by decreasing the frequency of collisions, because you move the container walls outward, right, you decrease the pressure, okay, which leads to a decrease in pressure. And so what happens is that the container walls will continue to move outwards until the internal and external pressures are equalized. Okay, so effectively what happens is that the volume changes to keep the internal and external pressure equal. All right, so that's what's happening, and we kind of went through that in a previous video, but that's how it works again. All right, let's continue on. Okay, so the opposite of this, of heating the gas, would be to cool the gas. Okay, and cooling the gas reduces the volume of a gas. Thus, if you cooled the gas down enough, in theory, you're supposed to get to a point where the volume of a gas reaches zero. Right? So you decrease the temperature, you decrease the volume. If you decrease the temperature enough, you'll get the volume to go down to zero. But that doesn't actually happen because we know that real gases are different to ideal gases. And when cooled sufficiently, they will turn into a liquid which have a fixed volume. All right? So, but that doesn't stop us from trying. So by experimentation, when gases are cooled, their volumes plotted on a graph, and that trend can be extrapolated. Okay, so what they did here was they took a whole bunch of samples of gases and they cooled them down, and they found that the volume decreased until a point where it turned into a liquid. Same with the oxygen, same with the argon. And what they found was that if you extrapolate after it, the volume, and after it turns into a liquid, you can still predict where it would have ended. And the point at where it would have ended is this point here at negative 273 degrees Celsius. All right, so with many different gases, the extrapolated trend showed that at a certain temperature, all the volumes of the gases would be zero, and that temperature was designated absolute zero at negative 273.15 degrees Celsius. Okay, so that's the idea of that you could cool something down enough for it to have zero volume, and that's the coldest that it could possibly be when the particles stop moving effectively. All right, so that's absolute zero, negative 273.15 degrees Celsius. However, the idea is that calculations can't really use negative values, because if you're doing calculations with negative values, it can lead to other negative values, right? And you can't have like negative number of moles, you can't have negative volume, that kind of stuff. So why should you be able to have negative temperatures? So if you consider temperature as a measurement of kinetic energy, these particles that are below 0 degrees Celsius don't really have negative energies. So what we need to do is we need to have a scale or a unit of temperature that does not have negative values and is related to the lowest temperature a substance can be. And so it should effectively start at that absolute zero. So they made up the scale, this dude called Lord Kelvin, and he named it after himself. The Kelvin Scale is a unit for temperature with no negative values and is related to the lowest temperature a substance can be. It effectively starts at, or 0 Kelvin is absolute zero. right? And to make it easier, because degrees Celsius was so convenient, each unit of K, or 1 Kelvin, is equal to 1 degree Celsius. All right, so they were like, screw Fahrenheit, because look at the difficulty of converting between Celsius to Fahrenheit, and look, the easy way to do it, right? Involving 5/9 of something, right? But the idea is that to convert between Celsius and Kelvin, then, because each unit of Kelvin is equal to 1 unit of degrees Celsius, right, all you got to do is add or subtract the 273.15, which is also found on your data sheet, so you don't have to memorize it, and therefore you can convert between Celsius and degrees Celsius and Kelvin quite easily. Right. A quick way of remembering whether you should add or subtract is that the K value must always be bigger than the C value. Right. So if you can't remember and you can't be bothered trying to remember it, you just have to remember K must always be larger. All right. And that's it for Charles's Law. Adios.